Hello, physical science. I'll be talking about calculating the mechanical advantage of different simple machines. But first of all, this is kind of a generic formula that we briefly talked about here to find the mechanical advantage, where you are taking the forces. All the others are measured in meters or centimeters. This one will be measured in forces. This is a generic one where I'll talk about lifting up a certain item, and that took so much effort to do it, and it is listed in newtons always for forces, and so that's how you would use this formula. It's kind of a generic one. It's the only one that they use forces on. Anyway, I just wanted to point out that again, resistance force is anytime that you're talking about the weight of an object, and applied force is your effort force, and that they are used simultaneously. So let's look at an example. Okay, what is the MA of a machine that lifts 100 newtons? So that's the object you're lifting with an effort of 20 newtons. So this was pretty nice. It's straightforward. Your effort that you just applied to it is the easiest one to see on it. Okay, because it even says effort right there. And so that is going to be 20 newtons. Okay, the resistance is the object that you're lifting, so that will be the 100 newtons. Okay, and then you'll go and calculate it, and you get that answer. Divide by 10, you get it to be 5. And there are no units because the newtons cancel out. So the mechanical advantage, this is 5. That means it's 5 times easier to use this machine than to do it without the machine. Okay, one of the first simple machines that we're going to talk about is the lever. And the lever has got 3 different parts to it. And the fulcrum is the point at which it pivots. Lever pivots. Okay, and the effort is your applied force. It's what you've applied to it. So you can use the word, when the word applied is in the story problem, then you can see that this is the one that you're talking about. And the resistance is always the mass, or the weight, I should say the weight that is the length of that. So this is the object you're lifting. Okay, anyway, so in every lever there is those 3 components, and you measure it from the fulcrum. For your formula to calculate MA, you measure it from the fulcrum. So the length of the effort is right here. Okay, and you measure from the center of mass of it. So this right here would be the length of your effort. The length of your resistance, however, goes from the fulcrum still to the middle of this mass, and that would be the length of your resistance. And then you would go and put the length of the effort over the length of the resistance, and that's how you would calculate the mechanical advantage. So let's look at a couple of different class levers. I always try to remember which one is in the middle, so that's how I did it to memorize, but you guys will get to use a cheat sheet on yours, but it will save you some time if you remember which is in the middle. The first class lever is like a seesaw, and it just pivots in the middle. Now the fulcrum could be way at the end. It could be closer to the resistance. You could move it over here. And if that's the case, then it would be like prying open a paint can lid. Your resistance is the lid, and here you're pivoting right on the edge of that can. And so this length could really be just about anywhere, because you'd be moving the fulcrum all along there. So the length of your effort, the length of your resistance could be really variable. And so the whole first class lever could have an MA of 1, greater than 1, or less than 1. Now the second class lever is arranged a little bit differently. The pivot point is at the very end. And so I try to just memorize these by just remembering that the resistance is in the middle. These are used for really heavy loads. And you'll notice that the length of your effort, okay, the length of your effort over the length of your resistance, the effort is really large compared to the resistance. So this right here has a very good mechanical advantage. And I think about a wheelbarrow or a trailer carrying horses. Okay, the pivot points are back by the wheels, or on the wheelbarrow the wheels, and then you got that heavy load, and then the tongue of your vehicle, or else your arms on the wheelbarrow are pulling them up. And that's how I remember the second class lever. The third class lever is arranged the one last way that can be arranged. The fulcrum is on the end again, but now the effort is in the middle. So these ones don't always have a really good mechanical advantage because the length of the effort is shorter than the length of the resistance. And so for these ones, it's really because it's more convenient, or it's just designed that way. So let's look at some pictures. A seesaw would be a first class lever, and a second class lever was the wheelbarrow, like I was talking about. And the third class lever would be a stapler. That's a really good example because the fulcrum is back here where the hinge is. You're applying effort, and the resistance is where the staple is. Now here's a whole bunch of examples. Why don't you stop for a second, go and guess a whole bunch of them, and I'm going to go and quickly write them on here. And so you can stop right now, and then you can quiz yourself and see which one is which. I'll put a 1, 2, and 3 on them. Stop. Okay, so those are the different classes of levers. Bring that information to me in class if you're confused about any of them, but on this one, I don't know if you can tell, but the pin for the hinge is right on the very end here. Okay. The wheel and axle is the second simple machine that we'll talk about. When you think about a screwdriver being a wheel and axle, it does have a mechanical advantage. A long time ago, they would have a really wide wooden handle, and they had a larger mechanical advantage because you put the radius of the wheel, this is the wheel of the screwdriver, over the radius of the axle. Now you can do diameter and diameter. You'd have the same exact one, but I think that they have just radius here so that it's easier to see if something's like a partial lever type wheel type thing, like our door handle. Anyway, if you go and look at the screwdriver, let's say that the handle is 4 centimeters wide, so that it's got a radius of 2 centimeters, and that the shaft has got a radius of a diameter of 1 centimeter, so let's just say it's 0.5 centimeters. Oops, that's centimeters. Anyway, so the mechanical advantage where the radius of the wheel, okay, is the screwdriver handle, and that is going to have a radius of 2 centimeters all over a radius of the axle, or the shaft in this case, where it's 0.5 centimeters, and so this is going to have a total mechanical advantage of 4. Again, the centimeters all cancel out, so you have no unit ever on mechanical advantage. And when we do our problems will have 3 points instead of 4 points when there's no unit. Okay, just 3 simple machines here. We only have one more left, and that's the pulleys. Anyway, these 3 simple machines are calculated with the same exact formula because they're all inclined planes. So for the ramp, the wedge, and the screw, you'd have to notice that like for example here, that the length of the ramp right here is 4 meters, and then the height of it is 2 meters. So this has a mechanical advantage. Let's set that up as the plane length over the plane height. So the plane length in this is 4 meters. Okay, and the height that they're lifting that bowling ball is 2 meters. And anyway, so it's going to have a mechanical advantage of 2. Okay, length over height. Now, the wedges are, the definition of a wedge is as 2 inclined planes back to back against each other if it's a wedge that's shaped like that. But you could figure out the mechanical advantage of that too. The definition of a wedge is that it splits something apart. Remember, I talked about in class that your bicycle seat splits your legs apart, so that is also a wedge too. But let's look at this too. Here is an inclined plane that is being wrapped around a screw. Okay, and so if you really think about it, you could put a thread around a screw, and you could figure out what is the height of the length of the plane. And you could also measure the height of the plane, and you could figure out the mechanical advantage. Moving on, the pulleys, here's 3 different types of pulleys. I'm going to go through this rather quickly, so you may have to rewind it. Anyways, there's a fixed pulley like you do when you hang up your deer when you're deer hunting. All it's doing is it's changing the load from going up instead you're pulling down. And these have a mechanical advantage of always of 1. So you need to write that down. It's got an MA of fixed pulleys is always 1. Movable pulleys have always got an MA of 2. Okay, and so they always have that. I don't know of too many instances where we use that except for like a zip line. The other kids were talking about that. But a block and tackle, the MA can really vary. So let's go over how we can figure that out. You can go and take all of the different forces here and divide them. So you would take 100 divided by 100, and you'd see that this fixed pulley has got an MA of 1. And that's true. And we've even talked about that. The only way that wouldn't be is if you've got a lot of resistance in your pulley wheel. Okay, now the next one, however, you can go and take these, the force of that divided by the force of this, you're going to find that has an MA of 2. But I'll tell you that there's a shortcut that always works too, and it works really well. It's not the number of wheels. Sometimes you'll notice that that's a common misconception that students have, but it's the number of pieces of the string that are attached to the wheel, to this weight assembly. There are 2 on this one, and so this makes this one an MA of 2. Now notice on this assembly of this block and tackle, the third one, that there's 1, 2, 3 that's attached to this weight assembly here. So this one has got an MA of 3. And you can go and prove it by dividing these. 100 divided by 33.5 would be 3. Now the last one, stop it and pause it now and guess what it is by counting those number of strings and then double checking by dividing the forces. Stop right now and I'm going to finish. So this one has got an MA of 4. There's 1, 2, 3, 4. Okay, and those ones are good examples because those are a number of pieces of strings that are attached to the weight assembly. And if you go and divide it, you'll see that that's true too. I've got another quick quiz on the next page, so go ahead and get that picture up and then pause it to quiz yourself, and I will write down the MAs of each one really quickly. Pause. And right now, I'm sure that you can see that's not exactly the number of wheels, because that last one is showing an example of where the first and last show examples where it's not the number of wheels, and that's a big misconception that students have. So I don't want you to fall for that, so that's the reason why I went and quizzed you with this one right here. You've got a worksheet to work on, and there's a discussion on the first page, and then you can skip that big rectangle section and complete that worksheet. See you later.